could 1,000 humans survive on Mars if Earth disappeared tomorrow? Mars looks beautiful in the photos, rusty dunes, ancient valleys, towering volcanoes, but beauty doesn't keep you alive. That stunning landscape is actually a radiation-soaked, freezing, airless hellscape that wants you dead. And here is a question. If you could ask the first Mars colonist anything about their experience, what would you ask? Comment down below. I'll pin the most creative answer. Now let's begin. Let me take you on a journey through the 6 monumental challenges that stand between humanity and Mars. The red planet itself is a world of extremes. It's roughly half the diameter of Earth, with about 38% of our planet's gravity. That might sound almost manageable until you realize what it means for everything from bone density to the behavior of liquids. Mars completes one rotation in about 24 hours and 37 minutes, giving it a day length eerily similar to Earth's. But that's where the similarities end. Mars has an atmosphere, but calling it that almost feels generous. The atmospheric pressure on Mars averages around 600 pascals, which is less than 1% of Earth's atmospheric pressure at sea level. To put that in perspective, that's equivalent to the atmospheric pressure you'd experience at an altitude of about 35 kilometers above Earth's surface, more than 3 times higher than commercial jets fly. This isn't just thin air. This is essentially the edge of space, and it gets worse. That wispy atmosphere is 95% carbon dioxide, with traces of nitrogen, argon, and less than 0.15% oxygen. You couldn't breathe it even if the pressure were adequate. The average surface temperature hovers around -63 degrees Celsius, though it can reach a balmy 20 degrees Celsius at the equator during summer days, only to plummet to -73 degrees Celsius at night. At the poles during winter, temperatures can drop to a bone-chilling -125 degrees Celsius. Now here's where it gets interesting from a physics standpoint. Because Mars has such low atmospheric pressure, water cannot exist in liquid form on the surface. If you poured a glass of water on Mars, it wouldn't freeze. Well, it might, depending on the temperature, but even if it were warm enough, it would boil away almost instantly. This is because water's boiling point isn't just temperature dependent, it's pressure dependent. On Earth at sea level, water boils at 100 degrees Celsius. On Mars, with its 600 Pascal atmosphere, water boils at temperatures near freezing. The phase diagram for water shows us that at Martian pressures, liquid water is essentially impossible. This isn't just inconvenient, it's a fundamental challenge that affects everything from agriculture to creating habitable spaces. But if you thought thin atmospheres and boiling water were our biggest problems, I have news for you. Those are just the opening act. The real challenges go much deeper, touching on the very nature of what it means to be human in an alien environment. Challenge number 1, radiation. Let's talk about the invisible killer that might be the single greatest obstacle to Mars colonization. Right now, you're being protected by something you probably never think about: Earth's magnetic field. Our planet functions as a giant magnet, generating a protective bubble called the magnetosphere that extends thousands of kilometers into space. This magnetic shield deflects most of the charged particles streaming from the Sun, particles that would otherwise strip away our atmosphere and bombard the surface with deadly radiation. We also have our thick atmosphere itself, which absorbs and scatters radiation that makes it past the magnetosphere. Mars has neither of these protections. About 4 billion years ago, Mars did have a magnetic field generated by a liquid iron core, just like Earth, but the Martian core cooled and solidified, and the magnetic field died. Without this protection, solar wind, a constant stream of charged particles from the Sun, has been stripping away Mars's atmosphere for billions of years. What remains is that thin, wispy layer of carbon dioxide we discussed. and with no magnetic field and almost no atmosphere, the Martian surface is exposed to radiation levels that would be lethal to humans over time. Let me give you some numbers from actual measurements. The Radiation Assessment Detector, or RAD, aboard NASA's Curiosity rover has been measuring radiation on Mars since August 2012. The data is sobering. On the Martian surface, astronauts would be exposed to approximately 0.65 millisieverts per day from galactic cosmic rays. That might not sound like much until you calculate what it means over time. For comparison, the International Space Station orbits within Earth's magnetosphere at an altitude of about 400 kilometers. Astronauts on the ISS experience roughly 0.6 millisieverts per day. Mars surface radiation is similar to the ISS, but here's the critical difference. ISS astronauts can return to Earth after 6 months or a year. Mars colonists would be exposed continuously for years, possibly decades, during a round trip to Mars, which would take roughly 3 years with current propulsion technology. 6 months to get there, 18 months waiting for the orbital alignment to return, and 6 months back, astronauts would accumulate a dose of approximately 1,000 millisieverts or 1 sievert. To put that in perspective, NASA's current career limit for astronauts is 600 millisieverts. The International Commission on Radiological Protection recommends a career limit of 1 sievert. A 3-year Mars mission would push astronauts right to or beyond these limits, and that's just from galactic cosmic rays, the constant background radiation from exploded stars throughout our galaxy. These are extremely high-energy particles, primarily protons, that travel at nearly the speed of light. They're incredibly difficult to shield against because they're so energetic that when they hit shielding material, they actually create secondary particles through a process called fragmentation. Sometimes the shielding makes the problem worse. Then there are solar particle events, or SPEs. These are massive eruptions from the sun that send intense bursts of radiation through space. If astronauts were caught in a major solar particle event without adequate shielding, they could receive a lethal dose of radiation in hours. The challenge is that we can't perfectly predict when these events will occur, though they're more common during solar maximum, the period of highest solar activity in the sun's 11-year cycle. If you're enjoying this deep dive into the science of Mars, please hit that subscribe button and give this video a like. We explore humanity's future in the stars together. Recent research published in 2021 examined the radiation risks from an extremely large solar particle event, similar to one that occurred in 993 or 994 AD, detected through elevated carbon-14 in tree rings and beryllium-10 in ice cores. Scientists estimated that if a similar event occurred during a Mars mission, astronauts could face life-threatening radiation exposure even with significant shielding. The biological effects of this radiation are complex and terrifying. High-energy cosmic rays damage DNA directly, creating double-strand breaks that can lead to cancer. But the effects go far beyond cancer risk. Studies suggest that cosmic ray exposure may cause cognitive impairment, damage to the cardiovascular system, cataracts, and damage to the central nervous system. Mouse studies have shown that even low doses of the type of radiation found in deep space can cause significant neurological damage, affecting memory and cognition. Think about what this means for Mars colonists. You're not just risking cancer in your old age. You're potentially facing cognitive decline that could impair your ability to perform the complex tasks necessary to survive on Mars. You're risking cardiovascular disease that could be fatal when the nearest hospital is 225 million kilometers away. You're facing a future where your biology is being altered at the cellular level every single day. The proposed solutions are currently inadequate. You could build habitats with thick shielding, burying structures underground or covering them with several meters of Martian regolith. This would help, but colonists would still need to go outside regularly for construction, repairs, and exploration. You could try to stay indoors during solar particle events, but that requires accurate forecasting and the ability to reach shelter quickly. Some researchers have proposed using water as shielding since hydrogen atoms are effective at absorbing radiation. Others have suggested magnetic shielding, creating an artificial magnetosphere around spacecraft or habitats. NASA announced in March 2026 a mission called Space Reactor 1 Freedom, set to launch in late 2028, which will test nuclear electric propulsion for a mission to Mars. While this technology could reduce transit time and therefore radiation exposure during the journey, it doesn't solve the fundamental problem of living on the Martian surface. The hard truth is this: with current technology, we cannot adequately protect humans from the radiation environment on Mars for the years or decades required to establish a permanent colony. Every day on Mars means rolling the dice with your long-term health. Every solar particle event is a potential death sentence. This isn't science fiction. This is physics, and physics doesn't negotiate. Challenge number 2. The human body is falling apart. Let me explain what I mean by that. Your body evolved over millions of years to function in one specific environment, Earth's surface, with its one gravitational field, its protective atmosphere, and its abundance of resources. Take a human out of that environment and place them on Mars with its 0.38 gravities, and things start going wrong. Not immediately, not catastrophically at first, but steadily, insidiously, in ways that compound over months and years. We've learned most of what we know about the effects of reduced gravity from astronauts on the International Space Station. In microgravity, essentially zero gravity, the human body undergoes dramatic changes. Bones lose density at a rate of 1 to 2% per month. Muscles atrophy despite rigorous exercise routines. The cardiovascular system weakens because the heart doesn't have to work as hard to pump blood. Fluids shift toward the head, causing vision problems that can become permanent. The immune system becomes compromised. Even the shape of the eyeball can change due to increased intracranial pressure. ISS astronauts exercise for roughly 2.5 hours every day, not for fitness, but for survival. Despite this intensive regime, they still lose significant bone and muscle mass. When they return to Earth after 6 months or a year, they can barely walk. They need assistance standing up. Their bodies have to readapt to Earth's gravity, a process that can take weeks or months. Some effects, particularly the vision changes, may be permanent. Now, Mars has gravity, 38% of Earth's. That's significantly more than the ISS's microgravity. But here's the terrifying question that nobody can definitively answer. Is 0.38 gravities enough to maintain human health long term? We simply don't know. We have extensive data on one gravity, Earth. We have growing data on zero gravity, the ISS, but we have almost no data on partial gravity. The Moon has 0.16 gravities, and the Apollo missions were far too short to study long-term effects. Mars is somewhere in between, and we're essentially guessing about what happens to human physiology. Some scientists are cautiously optimistic, suggesting that Mars's gravity might be sufficient to prevent the worst effects seen in microgravity. Others are deeply concerned, pointing out that even 38% gravity is a massive reduction from what our bodies need. Consider your skeleton. Your bones are constantly breaking down and rebuilding themselves through a process called remodeling. In normal gravity, the mechanical stress of supporting your body weight stimulates bone-building cells called osteoblasts. Reduce that stress, and bone formation slows while bone breakdown continues, resulting in net bone loss. The same principle applies to muscles. Without the constant resistance provided by Earth's gravity, Muscles have no reason to maintain their strength. Your heart, the most important muscle of all, would be pumping blood against significantly less gravitational resistance. Over years or decades, would a Martian colonist's cardiovascular system weaken to the point where returning to Earth becomes impossible? Would their bones become so fragile that even Mars's reduced gravity could cause fractures? And then there's pregnancy and child development, topics that rarely get discussed but are absolutely critical for any permanent colony. No human has ever been conceived, gestated, or born in space or on another planet. We have no idea if human reproduction would even be possible in reduced gravity. Animal studies have shown concerning results. Pregnant rats in microgravity experience developmental problems in their offspring. Would a fetus develop normally in 0.38 gravities? Would a child born on Mars, growing up in reduced gravity, develop a skeleton and cardiovascular system capable of supporting them? Or would they be forever trapped on Mars, their bodies too weak to ever experience Earth? Here's an even darker thought. If humans born on Mars cannot survive Earth's gravity, they become a separate branch of humanity, forever isolated on another world. The implications are profound, biologically, socially, philosophically. Recent discussions at NASA's Biological and Physical Sciences panel in August 2024 highlighted these exact concerns. Dr. Lisa Simonson, NASA's senior scientist for space radiation, emphasized that the combination of radiation exposure and reduced gravity creates a 1-2 punch for astronaut health. The radiation weakens cellular repair mechanisms, while the reduced gravity prevents normal tissue maintenance. Together, these factors could create cascade failures in human physiology. A Planetary Society article from June 2026 posed the question directly: are we ready to send humans to Mars? The author noted that while we could send humans to Mars with current rocket technology, whether they would survive and return to Earth is uncertain. More importantly, whether they could engage in vigorous exploration and scientific work. The whole point of sending humans instead of robots is deeply questionable. The psychological effects of reduced gravity are also poorly understood. Astronauts on the ISS report that after adapting to microgravity, they begin to feel normal. But they also describe a period of disorientation and sometimes nausea during the initial adaptation. How would the human brain adapt to Mars gravity permanently? Would depth perception change? Would motor control be affected? Would colonists find it increasingly difficult to coordinate movements as their brains rewire for a new gravitational environment? And we haven't even discussed the practical implications. In reduced gravity, everything behaves differently. Liquids form strange shapes. Dust doesn't settle the way it does on Earth. It hangs in the air longer, potentially creating respiratory hazards. Walking, running, and jumping all require relearning. Construction work becomes more challenging because materials don't have the same weight resistance. Even cooking becomes complicated when convection behaves differently. If you're curious about what daily life would actually be like for those first Mars colonists dealing with these gravity challenges and many others, I've created a detailed video exploring exactly that. Check out Why Your First Year on Mars Would Be the Hardest. It dives deep into the daily struggles, adaptations, and survival strategies that would define those crucial first months on the red planet. You'll find the link in the description and on the card above. Challenge number 3. The resource problem, or why Mars is a desert in space. Earth is abundant, absurdly, impossibly abundant. We have oceans covering 71% of the surface, an atmosphere rich in oxygen and nitrogen, soil teeming with nutrients and microorganisms, forests producing oxygen, ecosystems recycling waste, and a temperature range that allows liquid water to exist stably. We take this abundance for granted because we've never known anything else. Mars will teach colonists very quickly that abundance is not the universal default condition. Let's start with water, the most critical resource for human survival. The good news is that Mars has water, lots of it actually. The polar ice caps contain vast amounts of frozen water mixed with carbon dioxide ice. Subsurface ice exists at many locations, particularly at higher latitudes. NASA's Phoenix lander in 2008 directly sampled ice just beneath the surface. The Mars Reconnaissance Orbiter has mapped extensive ice deposits using ground-penetrating radar, but, and this is a crucial but, that ice isn't conveniently packaged and ready to use. It's mixed with Martian soil, called regolith. It's often buried beneath the surface, requiring excavation. It's frozen solid at temperatures far below 0 degrees Celsius. Extracting, purifying, and melting that ice requires significant energy, something that's also in short supply on Mars. Moreover, the distribution of ice isn't uniform. The most accessible ice deposits are at high latitudes, far from the equatorial regions where solar power is most abundant and temperatures are most moderate. This creates a fundamental tension. Do you build your colony where the ice is plentiful but the sunlight is scarce and temperatures are brutal? Or do you build where conditions are more moderate but water is harder to access? Even after you extract water, you face the boiling point problem we discussed earlier. At Martian atmospheric pressure, liquid water is unstable. It will either freeze or boil, depending on temperature. This means any water storage, processing, or transport must occur in pressurized containers. You can't have open reservoirs. You can't have streams or ponds. Every drop of water must be carefully contained and pressurized, adding layers of complexity and potential points of failure. Then there's oxygen. You and I are breathing roughly 21% oxygen in Earth's atmosphere right now without thinking about it. Mars's atmosphere is 0.15% oxygen, essentially none. Every breath a colonist takes on Mars must come from oxygen that's either brought from Earth or manufactured locally. The leading proposal for oxygen production is using a technology called MOXIE, Mars Oxygen in Situ Resource Utilization Experiment. MOXIE flew to Mars aboard the Perseverance rover and has been successfully producing oxygen from carbon dioxide in the Martian atmosphere since April 2021. The process works through solid oxide electrolysis, heating carbon dioxide to about 800 degrees Celsius and using electricity to split it into oxygen and carbon monoxide. MOXIE is a proof of concept, producing about 10 grams of oxygen per hour, enough to sustain one human for roughly 10 minutes. A full-scale system capable of supporting a crew of 4 to 6 people would need to produce approximately 25 to 30 kilograms of oxygen per day, accounting for breathing, life support system losses, and producing extra oxygen for rocket propellant to eventually return to Earth. Such a system would require substantial power, reliable operation in harsh Martian conditions, and continuous maintenance. Speaking of power, let's talk about energy. On Earth, we flip a switch and lights turn on. We have power grids fed by power plants burning fossil fuels, harvesting wind and solar energy, or using nuclear fission. We have abundant sunlight, roughly 1 kilowatt per square meter at the equator on a clear day. We have wind, flowing water, and geothermal heat. Mars has almost none of this. Solar power on Mars receives about 43% of the sunlight that Earth receives, roughly 590 watts per square meter at the equator. That's already a significant reduction, but it gets worse. Dust storms on Mars can last for weeks or even months, drastically reducing solar power generation. In 2018, a global dust storm covered the entire planet for weeks, blocking so much sunlight that the solar-powered Opportunity rover lost power and never recovered. Solar panels on Mars also face another challenge: dust accumulation. Martian dust is extremely fine and charged with static electricity, causing it to stick to surfaces. Unlike Earth, Mars has no rain to wash panels clean. Some dust devils, miniature whirlwinds, occasionally clean panels serendipitously, as happened several times with the Spirit and Opportunity rovers, but you can't build a power infrastructure based on hoping for fortuitous weather. The alternative is nuclear power. NASA's Space Reactor 1 Freedom mission, announced in March 2026, represents a major push toward nuclear electric propulsion and potentially nuclear surface power. The reactor would generate 20 kilowatts using highly enriched uranium. For reference, the average American household uses about 1 kilowatt of power continuously, or roughly 29 kilowatt hours per day. A Mars colony with habitat life support, oxygen production, water extraction and processing, manufacturing, research facilities, and communication systems would require many times that amount. Nuclear power solves the intermittency problem. It works day or night, dust storm or clear skies, but it comes with its own challenges: transporting nuclear fuel across interplanetary space, managing reactor heat in the thin Martian atmosphere, where convective cooling is nearly impossible, disposing of radioactive waste on a pristine planet, and maintaining complex nuclear systems with limited spare parts and expertise. Food is another monumental challenge. Every kilogram of food brought from Earth is enormously expensive. Current estimates suggest it costs roughly $10,000 to send 1 kilogram of payload to Mars. A human needs about 0.8 kilograms of food per day, or roughly 290 kilograms per year. For a crew of 6, that's 1,740 kilograms annually. Over a decade, you're looking at 17,400 kilograms of food, assuming no growth in colony size. The obvious solution is to grow food on Mars. But Martian agriculture faces obstacles that make even the most challenging farming conditions on Earth look easy. Let's start with the soil, or rather, the regolith, because calling it soil is misleading. Soil on Earth is a living ecosystem teeming with bacteria, fungi, worms, and organic matter. It's the product of billions of years of biological activity. Martian regolith is sterile, lifeless dust and rock that's been sitting under ultraviolet radiation for eons. The composition is also problematic. Martian regolith contains perchlorates, chlorine compounds that are toxic to humans and destructive to organic molecules. Concentrations vary by location, but measurements from the Phoenix lander found perchlorate levels around 0.5% by weight. Before you can grow anything, you'd need to wash or chemically treat the regolith to remove perchlorates, a process requiring significant water and energy. Even after cleaning the regolith and adding nutrients, you face the problem of growing conditions. Plants need light, and while Mars receives sunlight, it's not the same spectrum or intensity as Earth. You'd likely need to grow crops in pressurized greenhouses with supplemental artificial lighting, which demands even more precious electrical power. The thin atmosphere means you can't have open fields. Everything must be enclosed and pressurized. Temperature regulation in greenhouses becomes critical. As Martian surface temperatures swing wildly between day and night, pollination presents another challenge. On Earth, we have insects, birds, and wind to pollinate crops. Mars has none of these. Every plant requiring pollination would need manual or mechanical intervention. The time and labor requirements would be substantial. And here's a fact that really puts things in perspective. The International Space Station, with all its advanced technology and resupply missions from Earth every few months, still cannot produce enough food to fully support its crew. The vegetable production system, called Veggie, successfully grows small amounts of lettuce, radishes, and other crops in microgravity, but these are supplements, not staples. Astronauts still depend overwhelmingly on packaged food from Earth. If we can't achieve food self-sufficiency on the ISS, which is only 400 kilometers away with regular resupply, how do we expect to achieve it on Mars, which is millions of kilometers away with resupply windows every 26 months. The mathematics of self-sufficiency are sobering. Estimates suggest that to support one person year-round, you'd need approximately 200 to 500 square meters of growing space, depending on the crops and efficiency of your systems. For a colony of 100 people, you're looking at 20,000 to 50,000 square meters of pressurized, climate-controlled agricultural space. The construction alone would be a multi-year endeavor requiring enormous resources. But let's say you solve all of these problems. You extract water from ice, you produce oxygen from the atmosphere, you generate power from solar panels and nuclear reactors, you grow food in pressurized greenhouses. You've achieved the dream of living off the land, or living off the regolith, in this case. You're now facing challenge number 4, the communication and isolation problem. Right now, as you watch this video, if you wanted to call someone on the other side of Earth, you could do so instantly. If you sent a message, they'd receive it in milliseconds. We're connected through satellite networks, fiber optic cables, and cellular towers that span the globe. This connectivity isn't just convenient, it's become fundamental to how modern civilization operates. Mars colonists will experience isolation, unlike anything humans have known in the modern era. The speed of light, that ultimate cosmic speed limit, becomes your enemy. Light travels at 299,792 kilometers per second. At Mars's closest approach to Earth, roughly 55 million kilometers away, a radio signal takes about 3 minutes to make the journey. That means 6 minutes for a round-trip communication. You ask a question, wait 3 minutes for it to reach Earth. The person on Earth responds immediately, and you receive their answer 3 minutes later. At Mars's farthest distance from Earth, over 400 million kilometers away, that light travel time increases to about 22 minutes one way, or 44 minutes round trip. Imagine trying to have a conversation where there's a 44-minute delay between asking a question and hearing the response. Real-time communication becomes impossible. Video calls with loved ones back home turn into exchanges of recorded messages, more like emails than conversations. This isn't just emotionally challenging, it has profound operational implications. When the Apollo 13 mission experienced their life-threatening oxygen tank explosion, Mission Control in Houston was able to communicate with the crew in real time, working through problems as they emerged. The famous phrase, "Houston, we have a problem," led to immediate back-and-forth communication and collaborative problem-solving. On Mars, colonists wouldn't have that luxury. If something goes wrong, a life support system fails, someone gets injured, a critical piece of equipment breaks, they can't call Earth for immediate help. By the time Mission Control receives the distress signal and sends back instructions, between 6 and 44 minutes will have passed. In many emergency scenarios, that delay could mean the difference between life and death. This forces Mars colonists to be extraordinarily self-sufficient. Every person in the colony needs to be cross-trained in multiple disciplines. You can't specialize the way we do on Earth, where one person is a doctor, another is an engineer, and another is a farmer. On Mars, everyone needs to be a little bit of everything, because when something goes wrong, the expertise to fix it must exist within the colony. The psychological weight of this isolation cannot be overstated. Antarctica research stations provide the closest analog we have, and even those aren't truly comparable, because Antarctic researchers know they can be evacuated in a matter of hours or days if absolutely necessary. Mars colonists know they're 8 to 10 months away from Earth in the best-case scenario, and that's only during favorable orbital alignments. For roughly half of every 26-month cycle, returning to Earth is simply not an option regardless of the emergency. Studies of isolated environments on Earth submarines, Antarctic stations, remote research facilities have documented a phenomenon called the third quarter effect, where psychological strain peaks after about 3/4 of the way through a mission. People become irritable, depressed, and conflict-prone. Now extend that, not for months but for years or potentially a lifetime. The mental health challenges could be as threatening as the physical ones. Social dynamics become critical. Who do you send to Mars? What personality types can handle years of isolation and confinement with the same small group of people? How do you handle interpersonal conflicts when there's no escape, when you can't just quit your job and move to another city? The Antarctic Research Station at Vostok has a bar with a rule: no talking about politics, religion, or women, because those topics have historically led to fights in isolated conditions. Mars colonies would need similarly careful management of social dynamics, and there's a deeper, more existential aspect to this isolation. Every previous human explorer, no matter how remote their journey, could look up and see Earth. They were still part of the same planet, still connected by that profound sense of home. Mars colonists, looking up at the night sky, would see Earth as just another star. They would be the first humans truly separated from the home world, living on a fundamentally alien landscape where every breath, every drop of water, every morsel of food is the product of technological systems that must never fail. The philosopher Frank White coined the term overview effect to describe the cognitive shift astronauts experience when viewing Earth from space, a profound sense of awe and connection to our planet, a recognition of its fragility and beauty. Mars colonists might experience something entirely different, the alienation effect, a recognition of how far they've traveled from the only world that ever naturally supported human life, how dependent they've become on technology, and how thin the line is between survival and catastrophe. Challenge number 5, the technology and infrastructure gap. Even if we solved every biological and resource challenge, we still face a fundamental problem. We haven't built most of the technology necessary for Mars colonization. Let's talk about habitats. On Earth, buildings provide shelter from weather, maintain comfortable temperatures, and give us personal space. Mars habitats must do all of that while also providing air pressure, breathable atmosphere, radiation shielding, micrometeorite protection, and maintaining structural integrity in an environment that swings from relatively mild to brutally cold every single day. The leading designs involve either inflatable habitats, rigid prefabricated modules, or structures built using Martian regolith through a process called in situ resource utilization. Inflatable habitats like those being developed by Bigelow Aerospace and tested on the ISS offer the advantage of being lightweight during transport and expanding to large volumes once deployed. But they're vulnerable to punctures from micrometeorites or accidents and provide limited radiation protection unless buried under regolith. Rigid modules, similar to the International Space Station components, are proven technology but are heavy to transport and limited in size by rocket-faring dimensions. The ISS took over a decade to assemble with multiple launches, and it orbits just 400 kilometers from Earth, with resupply missions every few months. Building equivalent infrastructure on Mars would be exponentially more challenging. The most promising approach might be using Martian regolith itself as a building material. Proposals include 3D printing structures using regolith mixed with binding agents, creating bricks from compressed regolith, or even melting regolith using solar concentrators or microwaves to form solid structures. NASA's Centennial Challenges program has run multiple competitions for Mars habitat designs, with winning entries featuring creative use of local materials. But these technologies remain largely theoretical or tested only in small-scale demonstrations. We haven't built a full-scale Mars habitat and tested it under actual Martian conditions for years at a time. We don't know how these structures will hold up to dust storms, temperature cycling, radiation exposure, and the subtle but constant challenges of the Martian environment. Transportation infrastructure is another massive gap. Getting to Mars is one thing. We've sent numerous robotic missions successfully. But those missions carried payloads measured in hundreds of kilograms, or, at most, a few tons. The Perseverance rover weighs about 1,025 kilograms. The Curiosity rover weighs roughly 899 kilograms. These are sophisticated machines, but they're tiny compared to what human missions require. A crewed mission to Mars would need to transport not just the crew, but also their habitat, life support systems, food, water, equipment, and fuel for the return journey. We're talking about payloads of hundreds of tons. No currently operational rocket can launch that much mass to Mars in a single mission. SpaceX's Starship, still under development, is designed to carry 100 tons to Mars, but as of June 2026, it's still in testing phases and has not yet achieved a successful orbital flight with payload deployment and recovery. Even if Starship or a similar heavy lift vehicle becomes operational, you'd need multiple launches to establish even a basic colony. Each launch represents enormous expense and risk. And here's a reality check. SpaceX announced in February of this year that it was delaying its Mars ambitions by several years to focus on lunar missions. The company recognized that the technology readiness level for Mars missions is significantly lower than originally anticipated. Once on Mars, colonists need transportation across the surface. The rovers we've sent, Spirit, Opportunity, Curiosity, and Perseverance, travel at speeds of about 0.14 kilometers per hour. That's slower than most people walk. They're designed for careful, methodical exploration, not efficient transportation. A human colony would need vehicles capable of traveling tens or even hundreds of kilometers to access resources, explore, and conduct research. These vehicles must operate in an environment with no roads, no fuel stations, no repair shops, and no rescue services. They must handle terrain ranging from dusty plains to boulder fields to steep crater walls. They must protect occupants from radiation during longer journeys. They must carry life support equipment, since any vehicle excursion is essentially a mobile habitat. And they must be maintained with limited spare parts and tools. NASA and other agencies have proposed various rover designs, from pressurized vehicles that allow astronauts to work in shirt sleeves to unpressurized rovers that require occupants to wear spacesuits throughout the journey. But again, these remain largely concepts and prototypes. We haven't field-tested Mars vehicles under actual Martian conditions for the thousands of kilometers of operation that a colony would require. Then there's manufacturing and repair infrastructure. On Earth, when something breaks, you order a replacement part. It arrives in days, sometimes hours. That supply chain represents centuries of industrial development, mines extracting raw materials, factories refining and processing them, manufacturing facilities producing components, distribution networks delivering them globally. Mars has none of this. Every spare part, every tool, every replacement component must either be brought from Earth or manufactured on Mars. The mass and volume constraints of interplanetary transport mean you can't possibly bring everything you might need. Instead, you need manufacturing capabilities, 3D printers, machine shops, electronics fabrication. That can produce parts from raw or recycled materials. The concept is called in situ resource utilization and manufacturing, and it's critical for long-term sustainability. You need to be able to produce everything from simple bolts and brackets to complex electronic circuits and medical equipment. Some of these capabilities are emerging. The ISS has 3D printers that can produce plastic parts in microgravity. Researchers are developing techniques to extract metals from Martian regolith using electrolysis or other processes. But we're talking about recreating on Mars with limited resources and personnel manufacturing capabilities that took human civilization thousands of years to develop on Earth. Even simple materials we take for granted, plastics, metals, glass, ceramics, require complex chemical processes, often needing specific temperatures, pressures, and catalysts. Can you manufacture high-quality steel on Mars? Can you produce the semiconductors necessary for computer chips? Can you create the pharmaceuticals needed for medical treatment? Each of these questions represents not just a technological challenge, but an entire field of research. Materials science under Martian conditions is largely unexplored. We don't know how metallurgy works in reduced gravity and different atmospheric composition. We don't know how chemical processes are affected by the Martian environment. We're essentially trying to recreate industrial civilization from first principles in an alien environment. Medical infrastructure presents particularly acute challenges. On Earth, when someone gets seriously ill or injured, we have hospitals with imaging equipment, surgical facilities, intensive care units, and pharmacies stocked with thousands of medications. A Mars colony would have, at best, a small medical bay with limited equipment and a constrained pharmacy. What happens when someone needs surgery? The colony's doctor, assuming you have someone with surgical training, would need to operate with whatever equipment and supplies are available. No consulting specialists in real time, no rush ordering specialized equipment, no transferring the patient to a better equipped facility. You work with what you have or the patient dies. What about diseases? The colony would presumably screen members carefully and quarantine rigorously to prevent bringing pathogens from Earth. But human bodies contain trillions of microorganisms, and those populations can change and evolve. What if someone develops a resistant bacterial infection? Do you have the antibiotics needed? What if someone has an appendicitis? Can your doctor perform an appendectomy with the equipment available? Pregnancy and childbirth represent even greater medical challenges. We discussed earlier the unknown effects of reduced gravity on fetal development, but even assuming pregnancy proceeds normally, childbirth is inherently risky. On Earth, even with modern medicine, complications occur. On Mars, with limited medical resources and no possibility of emergency evacuation, those complications could easily be fatal. Mental health care is another critical need that's often overlooked. The psychological stress of Mars colonization, the isolation, the confinement, the constant danger, the separation from Earth, would inevitably affect colonists' mental health. Depression, anxiety, interpersonal conflicts, and potentially more severe psychological issues would require treatment. But therapy requires either trained psychologists within the colony or remote therapy sessions with Earth-based therapists dealing with communication delays of 6 to 44 minutes. Psychiatric medications would need to be stockpiled, with no ability to quickly obtain new prescriptions. Communication infrastructure is also more complex than it might initially seem. We've discussed the light delay problem, but there's also the question of maintaining communication systems. Earth and Mars need to maintain radio contact through a network of satellites and ground stations. NASA's Deep Space Network, the collection of radio antennas in California, Spain, and Australia that communicate with deep space missions, would be essential for Mars colonization. But the Deep Space Network is already overburdened, supporting dozens of missions throughout the solar system. Adding regular, high-bandwidth communication with a Mars colony would strain its capacity. You'd likely need dedicated Mars communication satellites, both orbiting Mars and possibly at Lagrange points between Earth and Mars, creating a relay network. These satellites would need to be launched, maintained, and eventually replaced. Space-based infrastructure fails, solar panels degrade, electronics break down, orbits decay. Without the ability to repair or replace satellites, communication infrastructure gradually deteriorates. A Mars colony might find itself increasingly isolated, not by distance but by failing technology. Energy storage is another critical infrastructure gap. We've discussed power generation through solar panels or nuclear reactors, but Mars colonists also need to store energy for use during dust storms, at night, or during peak demand periods. On Earth, we use batteries, pumped hydro storage, compressed air energy storage, and other methods. Mars needs similar capabilities, but with technology that can operate in extreme cold and reduced atmospheric pressure. Current battery technology struggles at Martian temperatures. Lithium-ion batteries, the current standard for energy storage, have reduced performance and can fail at the temperatures commonly experienced on Mars. Researchers are developing cold-resistant battery chemistries, but these remain in early development stages. Other energy storage methods, flywheels, compressed gas systems, even hydrogen fuel cells, each have their own challenges in the Martian environment. The infrastructure requirements extend to waste management, water recycling, atmospheric processing, resource extraction, manufacturing, transportation, communication, medical facilities, research laboratories, agricultural systems, and habitation. Each system must be reliable, maintainable with limited resources, and resilient to the harsh Martian environment. Each system represents years or decades of development, testing, and refinement. And here's the uncomfortable truth. We haven't built these systems yet. We have concepts, proposals, prototypes, and small-scale demonstrations. But we don't have flight-ready, Mars-proven technology for most of these critical systems. The gap between what we have and what we need is measured not in years but in decades of intensive research, development, and testing. Challenge number 6, the economic reality. Let's talk about money, because ultimately, Mars colonization isn't just a technical challenge, it's an economic one. The Apollo program, which put 12 humans on the Moon for a total of about 300 hours, cost approximately $157 billion in today's currency. That's $157 billion to achieve brief visits to a world 3 days away, with missions lasting at most 12 days on the surface. Mars is orders of magnitude more challenging, more distant, and requires far longer mission durations. Estimates for the cost of sending humans to Mars vary wildly, from NASA's estimates of hundreds of billions of dollars to private sector claims of lower costs through reusable rockets and innovative technology. But even the most optimistic estimates put a crewed Mars mission at tens of billions of dollars. And that's just for a single mission, essentially a flags and footprints expedition like Apollo. Establishing a permanent, self-sustaining colony would cost far more. You're talking about multiple launches over many years, building extensive infrastructure, supporting a growing population, and continuing resupply missions until the colony achieves self-sufficiency, if it ever does. Some economists have suggested the total cost could reach into the trillions of dollars over several decades. Where does this money come from? Government space agencies have limited budgets. NASA's entire budget for fiscal year 2026 is approximately $25 billion, and that must cover not just Mars exploration, but also the International Space Station, Earth science, aeronautics research, technology development, and numerous other programs. The European Space Agency, Roscosmos, JAXA, and other national agencies face similar budget constraints. Private companies like SpaceX, Blue Origin, and others are investing in space technology, but they ultimately need a business model. They need a way to make money, or at least a compelling reason for investors to continue funding operations. SpaceX makes money by launching satellites and cargo to the ISS. They've received significant funding from NASA contracts, but Mars colonization doesn't have an obvious revenue stream. Some people propose mining asteroids or Mars itself for valuable resources to sell back on Earth. But the economics are challenging. Yes, asteroids contain metals like platinum that are valuable on Earth. But the cost of extraction, processing, and returning those materials to Earth would be enormous. You'd need to bring those materials back down Earth's gravity well through atmospheric re-entry to manufacturing centers, all while competing with terrestrial mining that's far cheaper and more established. Mars itself has no unique resources that Earth lacks. Anything you can mine on Mars exists on Earth or on asteroids closer to Earth. The Martian environment doesn't enable easier manufacturing, quite the opposite. There's no product you could manufacture on Mars and profitably sell on Earth that wouldn't be cheaper to make on Earth itself. Tourism has been suggested as a potential revenue stream, but the economics remain questionable. Space tourism to low Earth orbit, a mere few hundred kilometers away, costs tens of millions of dollars per person with companies like SpaceX and Blue Origin. A trip to Mars would cost exponentially more, take 8 to 10 months each way, expose tourists to life-threatening radiation and health risks, and offer an experience that, while historic, would be characterized more by confinement and discomfort than luxury. How many people would pay potentially hundreds of millions of dollars for such an experience? How many could afford it? Even if you found a few ultra-wealthy individuals willing to make the journey, that's not a sustainable economic model for establishing and maintaining a colony of hundreds or thousands of people. Some proponents argue that Mars colonization doesn't need to be economically profitable in the conventional sense. They suggest it's an investment in humanity's future, a form of insurance against extinction-level events on Earth, or a manifestation of our species' innate drive to explore. These are compelling philosophical arguments, but they don't solve the practical problem of funding. Money must come from somewhere, whether government budgets, private investment, or some combination of both. The International Space Station provides a cautionary example. The ISS has cost roughly $150 billion over its lifetime, split among NASA, Roscosmos, ESA, JAXA, and the Canadian Space Agency. It's been continuously occupied since November 2000, providing invaluable research and operational experience. But it's also enormously expensive to maintain, requiring regular resupply missions and eventually facing decommissioning as components age. The ISS is only 400 kilometers away. Resupply missions take hours, not months. If something breaks, new parts can arrive within weeks. Crew can be evacuated in emergencies. Despite these advantages and the involvement of multiple wealthy nations, the ISS is barely sustainable economically, with periodic debates about whether to continue funding it. Now imagine trying to sustain a similar outpost on Mars, millions of kilometers away, with resupply windows every 26 months and no possibility of emergency evacuation. The economic challenge becomes staggering. There's also the opportunity cost to consider. The money spent on Mars colonization could fund other priorities: climate change mitigation, disease research, education, poverty reduction, or even other space exploration efforts that might yield more immediate scientific returns. Every dollar spent on Mars is a dollar not spent on something else. I'm not arguing that Mars colonization isn't worthwhile. I personally find it one of the most inspiring endeavors humanity could pursue, but we need to be realistic about the economic challenges. Unless we develop new economic models, identify revenue streams we haven't yet imagined, or achieve breakthrough technologies that dramatically reduce costs, the financial barriers to Mars colonization may prove as insurmountable as the technical ones. Challenge number 7, the social and political dimensions. Human space exploration doesn't happen in a vacuum. It's embedded in complex social, political, and ethical contexts that can enable or prevent it. The Apollo program succeeded in part because it occurred during the Cold War, when space achievement was viewed as a proxy for geopolitical power and ideological superiority. The United States invested enormous resources not primarily for scientific advancement, but to demonstrate technological and organizational supremacy over the Soviet Union. Once that goal was achieved with the moon landings, political support and funding evaporated. We haven't sent humans beyond low Earth orbit since 1972, over half a century ago. Current geopolitical dynamics are different. While there's renewed space competition between the United States, China, Russia, and increasingly other nations like India and the United Arab Emirates, the dynamics aren't the same as the Cold War space race. Space programs today must compete for funding and political attention with numerous other priorities in an era of constrained budgets and polarized politics. Public support for space exploration is often shallow. Polls typically show majorities supporting space exploration in principle, but when asked whether they'd support increased funding, support drops dramatically. Space exploration competes with immediate concerns: healthcare, education, infrastructure, national defense, and in democratic societies, politicians respond to voter priorities. International cooperation could help share costs and risks, but it also introduces complexity. The International Space Station Partnership, while successful, required decades of negotiation and compromise. Different nations have different priorities, capabilities, and risk tolerances. Coordinating a Mars colonization effort among multiple countries would require unprecedented levels of international cooperation, sustained over decades, a challenging proposition in our current geopolitical climate. There are also ethical questions that society hasn't fully grappled with. Do we have the right to colonize Mars, potentially contaminating a pristine environment with Earth life? The Outer Space Treaty of 1967 requires that space exploration be conducted in a manner that avoids harmful contamination of celestial bodies, but what constitutes harmful contamination is subject to interpretation. Mars may be lifeless now, but it might contain evidence of past life, or even microbial life existing in protected subsurface environments. Would establishing a human colony with inevitable biological contamination destroy evidence that could answer one of humanity's most profound questions? Are we alone in the universe? Some astrobiologists argue we should explore Mars extensively with robots first, thoroughly searching for any signs of past or present life, before committing to human missions that would irreversibly alter the Martian environment. Then there are questions about governance. Who would govern a Mars colony? Would it be under the jurisdiction of Earth governments, or would colonists establish their own governance structures? The Outer Space Treaty states that nations retain jurisdiction over their space objects and personnel, but how does this apply to a permanent, growing colony with people from multiple nations, plus potentially children born on Mars who might claim Martian rather than terrestrial citizenship? History provides sobering lessons about colonization. European colonization of the Americas, Africa, and other regions involved exploitation, conflict, and tremendous suffering, while Mars colonization wouldn't involve displacing indigenous populations. As far as we know, Mars is lifeless. Other problems could emerge. Would Mars colonies be egalitarian communities, or would they reproduce Earth's inequalities? Who gets to go to Mars, and based on what criteria? Would wealth determine access, creating a scenario where only the rich can escape Earth? Would Mars become a refuge for the privileged while Earth faces climate change and resource depletion? These might seem like distant concerns, but they shape public support and political will today. If Mars colonization is perceived as a vanity project for billionaires, While Earth faces existential challenges, political support will evaporate. If it's seen as abandoning Earth rather than protecting humanity's future, it will face opposition. Religious and philosophical perspectives also matter. Some people view space exploration as humanity's destiny, a fulfillment of our drive to explore and expand. Others see it as hubris, an arrogant assumption that we have the right to spread across the cosmos. Some religious traditions embrace space exploration as exploring God's creation. Others might view terraforming Mars, intentionally altering its environment to make it more Earth-like, as playing God inappropriately. These aren't abstract debates. They influence policy, funding, and the social consensus necessary for long-term projects. Mars colonization would require sustained commitment across decades, spanning multiple political administrations and potentially weathering changes in public opinion. Maintaining that commitment through economic recessions, political upheavals, and competing crises would be extraordinarily difficult. There's also the question of what happens if things go wrong. If a Mars mission fails catastrophically, with crew deaths broadcast across global media, public and political support could collapse. The Space Shuttle Challenger disaster in 1986 and Columbia disaster in 2003 each led to multi-year suspensions of shuttle flights and intense scrutiny of NASA's programs. A similar disaster on Mars, with even more dramatic loss of life and potentially colonists stranded with no hope of rescue, could set space exploration back decades. Challenge number 8, the biological unknowns. Despite all our scientific advancement, we remain profoundly ignorant about how life, especially human life, functions in environments radically different from Earth. We've discussed reduced gravity's effects on bones, muscles, and the cardiovascular system, but there are deeper biological questions we can't yet answer. How does reduced gravity affect cellular function at the molecular level? Does gene expression change? Do cells repair DNA damage as effectively in low gravity as they do in terrestrial gravity? Research on the ISS has revealed that microgravity affects gene expression, cellular signaling, and even the shape of cells. Some bacteria become more virulent in microgravity. They grow faster, form more robust biofilms, and become more resistant to antibiotics. The exact mechanisms aren't fully understood, but the implications are concerning. Would Martian gravity have similar effects? Would normally benign bacteria become dangerous? Would infections be harder to treat? The immune system appears to be compromised in space. Studies of astronauts show changes in immune cell function, reduced immune response, and reactivation of dormant viruses like herpes. Some astronauts develop rashes or other immune-related problems during missions. On Earth, these would be minor inconveniences. On Mars, with limited medical resources, a compromised immune system could be life-threatening. Wound healing might also be affected by reduced gravity. On Earth, gravity influences how fluids move through tissues, how blood clots form, and how new tissue develops during healing. In altered gravity, these processes might not work as efficiently. A wound that would heal normally on Earth might become a serious medical problem on Mars. Human reproduction in space or on Mars remains almost entirely unexplored territory. No mammals have completed a full life cycle, conception through birth through maturity, in space. The few experiments conducted with rodents, amphibians, and other species have shown concerning results. Mouse embryos developed abnormally in microgravity. Salamanders in space showed inner ear abnormalities. Fruit flies born in space had trouble orienting themselves in gravity later. Would human sperm function normally in Martian gravity? Would eggs fertilize properly? Would the embryo implant correctly in the uterine wall? Would fetal development proceed normally? Or would the reduced gravity cause developmental abnormalities? These aren't just academic questions. If humans cannot reproduce successfully on Mars, then true colonization, as opposed to temporary occupation, becomes impossible. Even if pregnancy proceeds normally, childbirth presents unique challenges. Labor and delivery are affected by gravity. It influences how the baby moves through the birth canal, how effectively contractions work, and how blood circulation is maintained. In reduced Martian gravity, would these processes work the same way? Would complications be more likely? Would cesarean sections become necessary more often, requiring surgical capabilities that might not be available? And if a child is born on Mars and develops normally, what happens if they ever want to visit Earth? Their body would have developed in 0.38 Earth gravity. Their bones, muscles, and cardiovascular system would be adapted to Martian conditions. Coming to Earth would subject them to nearly 3 times the gravity they're accustomed to. They might not have the bone density or muscle strength to stand, walk, or even sit upright in Earth's gravity. They could be effectively trapped on Mars, unable to ever visit the homeworld of their species. This creates a profound ethical dilemma. Do parents have the right to have children on Mars, knowing those children might be unable to ever experience Earth? Is it ethical to create a human being who would be biologically adapted to Mars, but unable to survive on the planet where humanity evolved? Neurological development is another unknown. Human brains develop through childhood and adolescence in response to environmental stimuli, including gravity. The vestibular system, our sense of balance and spatial orientation, relies on gravity to function. Children born and raised in Martian gravity would have vestibular systems calibrated to that environment. How would this affect their cognitive development, spatial reasoning, or motor skills? We don't know, because we've never had a child develop in reduced gravity. There are also questions about circadian rhythms. Human biology is synchronized to Earth's 24-hour day through complex interactions between light exposure, hormones like melatonin, and internal biological clocks. Mars has a slightly longer day, 24 hours, 39 minutes, and 35 seconds. This might seem like a trivial difference, but circadian disruption is associated with sleep disorders, mood problems, cognitive impairment, and long-term health issues. Would humans successfully adapt to the Martian day length, or would we constantly be slightly out of sync with the day-night cycle, accumulating sleep debt and circadian stress? Some research suggests humans can adapt to slightly longer days, but we've never tested this over years or lifetimes. The cumulative effects of chronic circadian disruption could be significant. Nutrition presents another biological unknown. We understand human nutritional needs on Earth fairly well, but would those needs change in Martian gravity and radiation environment? Some nutrients might be metabolized differently. The body's calcium balance, already disrupted by reduced gravity, might require different nutritional approaches. The energetic demands of living in spacesuits, maintaining body temperature in a cold environment, and dealing with environmental stresses might change caloric and nutrient requirements. Plants grown on Mars in Martian regolith, even after cleaning and treatment, might have different nutritional profiles than crops grown on Earth. Mineral content, vitamin levels, and the presence of anti-nutrients or potentially harmful compounds could all vary. We've seen hints of this in ISS experiments, where plants grown in space sometimes have different chemical compositions than their Earth-grown counterparts. The psychological effects of permanently living in an artificial environment also qualify as biological unknowns, since psychology is ultimately rooted in neurobiology. Every human who has ever lived has experienced rain, wind, natural sunlight, the smell of earth after rain, the sound of birds or insects, the sight of clouds moving across a blue sky. These experiences are part of what it means to be human. They've shaped our evolution, our culture, and our psychology. Mars colonists would live in pressurized habitats, breathing recycled air, drinking recycled water, eating crops grown under artificial lights. They might go weeks or months without experiencing anything natural. Everything around them would be artificial, manufactured, maintained by technological systems. They would never feel natural wind on their face outside a spacesuit. They would never hear natural sounds beyond the human colony. They would never see Earth's blue sky or white clouds. We don't fully understand what this sensory deprivation and artificial environment would do to human psychology over years or decades. Antarctic research stations and submarines provide some insight, but even those environments are temporary and still within Earth's ecosystem. Mars would be permanent and completely artificial. The term environmental generational amnesia describes how each generation perceives the environment they grew up in as normal, even if it's degraded compared to previous generations. Children born on Mars would have no direct experience of Earth's environment. They would grow up thinking life in pressurized habitats, recycled air, and Martian landscapes is normal. What would this do to human psychology across generations? The microbiome, the trillions of bacteria, fungi, and other microorganisms that live in and on our bodies, is another biological frontier we barely understand. These microorganisms aren't just passengers, they're essential to our health. They help digest food, produce vitamins, train our immune systems, and influence everything from mood to disease resistance. The human microbiome is shaped by our environment. Different populations on Earth have characteristic microbiomes influenced by diet, lifestyle, and environmental exposure. What happens to the microbiome in the sealed, artificial environment of a Mars colony? With no environmental exposure, with recycled everything, with limited food diversity, would the microbiome change in ways that affect health? Research on the ISS has shown that the microbial ecology of the station changes over time, with certain organisms becoming dominant. Some of these are potentially pathogenic, and they develop antibiotic resistance. The ISS has connection with Earth through regular resupply and crew rotation, bringing microbial diversity from Earth. A Mars colony, especially as it becomes more self-sufficient, would become increasingly isolated microbiologically. The confined environment could select for particular microorganisms, potentially creating a unique Martian microbiome, one we know nothing about and can't predict. There's also forward contamination to consider. Humans are walking biospheres, carrying trillions of microorganisms. Despite sterilization efforts, we'd inevitably bring Earth life to Mars. Some of these organisms might find niches in the Martian environment, particularly in and around habitats where temperature, pressure, and moisture are more hospitable. Could Earth microorganisms establish themselves in Martian soil near habitats, spread to natural Martian environments, and fundamentally alter the planet's pristine state? The possibility of back contamination, bringing Martian material that might contain unknown organisms back to habitats or, eventually, to Earth is another concern. Mars might not have life, but if it does, we'd be introducing completely alien biology to human environments. The consequences are impossible to predict. Could Martian microorganisms infect humans? Probably not. They'd be adapted to completely different biochemistry. But we can't be certain without actually finding Martian life and studying it. All of these biological unknowns represent not just knowledge gaps but actual risks. When we send humans to Mars, we're conducting an experiment with human subjects in an uncontrolled environment with no ability to stop the experiment if things go wrong. This raises profound ethical questions about informed consent, acceptable risk, and the responsibility we have to colonists and their potential children. Challenge number 9. The technological reliability problem. Even if we develop all the technology necessary for Mars colonization, it must be extraordinarily reliable in an environment where failure means death. Think about technology in your daily life. Your phone occasionally crashes, your computer has glitches, your car might break down. These are annoyances on Earth because you can usually work around them. You restart the device, you call a repair service, you get a ride from someone else. On Mars, technological failure isn't an annoyance. It's potentially catastrophic. The life support system must work continuously without fail. If oxygen generation stops, colonists have hours to fix it before they asphyxiate. If water recycling fails, they have days before dehydration becomes critical. If heating fails, they could freeze. If the habitat loses pressure, they have seconds to get into spacesuits or they die. Compare this to the International Space Station, which has had numerous close calls. In 2021, the ISS experienced an uncontrolled spin when a Russian module's thrusters unexpectedly fired. In 2018, a small hole, possibly caused by a manufacturing defect or accidental drill damage, caused a slow pressure leak. In 2020, the station's oxygen generation system failed and had to be repaired. In each case, the crew was able to resolve the problem, sometimes with real-time assistance from ground control on Earth. The ISS benefits from redundant systems, regular resupply with spare parts, and the ability to evacuate the crew if necessary. Mars colonists wouldn't have these advantages. Communication delays prevent real-time assistance. Resupply missions arrive every 26 months at best. Evacuation would take 8 to 10 months and might not be possible depending on orbital alignments. This requires a level of reliability far beyond what we typically achieve with technology. Industrial systems on Earth aim for reliability figures like 3 nines, 99.9% uptime, meaning about 9 hours of downtime per year. Critical systems might achieve 4 nines or even 5 nines, but these figures still allow for some failure because Earth's environment provides buffers. You can survive hours without electricity. You can get by for days without certain systems. Mars life support systems need to approach perfect reliability. 6 nines or better, meaning less than 32 seconds of downtime per year. And this reliability must be maintained, not with cutting-edge technology fresh from the factory, but with systems that are years old, subjected to Martian dust, temperature extremes, and radiation, maintained by non-specialists with limited tools and spare parts. Achieving this level of reliability requires multiple redundant systems. If one oxygen generator fails, you need a backup. But the backup also needs a backup, because on Mars you can't risk a single point of failure. This redundancy adds mass, volume, complexity, and cost to every system. It also adds maintenance burden. More systems means more things that need regular inspection, calibration, and eventual replacement. There's also the problem of common mode failures, situations where multiple redundant systems fail for the same reason. On Earth, this might be a power grid failure that takes down multiple backup systems, or a software bug that affects all systems running the same code. On Mars, a dust storm might reduce solar power to all systems simultaneously. A radiation event might damage electronics across multiple systems. A manufacturing defect might affect multiple components that were all produced in the same batch. Protecting against common mode failures requires not just redundancy but diversity. Having backup systems that work on different principles, use different technologies, or draw power from different sources. This further increases complexity, cost, and maintenance requirements. Software presents particular challenges. Modern systems rely heavily on software, which is notoriously difficult to make perfectly reliable. A single coding error, an unexpected input, or an unforeseen interaction between systems can cause crashes or incorrect behavior. On Earth, software bugs are routine. We've grown accustomed to updates, patches, and occasional failures. On Mars, a software bug in a critical system could be lethal. NASA and other space agencies use extensive testing, formal verification methods, and conservative design approaches to maximize software reliability. But even with these measures, bugs slip through. The Mars Polar Lander was lost in 1999, possibly due to a software error that shut down its engines prematurely during landing. The Ariane 5 rocket failed on its maiden flight in 1996 due to a software error related to integer overflow. These are organizations with rigorous quality control and testing, yet failures still occur. A Mars colony would need to update and modify software over time as needs change and issues are discovered. But how do you safely update software on systems where failure means death? You need extensive testing in a simulated environment, careful rollout procedures, and the ability to quickly roll back changes if problems emerge. All of this requires expertise, infrastructure, and resources that might not be available in a small, isolated colony. Hardware faces similar challenges. Electronic components degrade over time, especially when exposed to radiation. Mechanical parts wear out. Materials become brittle or corroded. On Earth, we handle this through preventive maintenance programs, regularly replacing components before they fail based on statistical reliability data. But on Mars, you can't rely on regular shipments of replacement parts. You need to either bring enough spares to last for years, or manufacture replacement parts locally, which brings us back to the industrial infrastructure challenges discussed earlier. The concept of mean time between failures, MTBF, becomes critical. If a component has an MTBF of 10,000 hours, about 14 months, and your life support system depends on 10 such components, you can expect a component failure every 6 weeks on average. Even with redundancy, you'd be constantly repairing and replacing parts, assuming you have the spares and expertise available. More reliable components typically cost more, weigh more, or perform less efficiently. There's a constant tension between reliability, mass, cost, and performance. Launch mass is expensive. Every kilogram sent to Mars costs thousands or tens of thousands of dollars. Using more reliable but heavier components means fewer total systems, less redundancy, or more launches. Using lighter but less reliable components means more frequent failures and higher spare parts requirements. Testing is another challenge. On Earth, we can test systems extensively under realistic conditions before deploying them. We can conduct years of operational testing, identify failure modes, and refine designs. But we can't perfectly replicate Martian conditions on Earth. We can simulate reduced gravity, but not for extended periods. We can simulate temperature and pressure in chambers, but not at the scale of an entire habitat. We can expose materials to simulated Martian radiation, but not while simultaneously subjecting them to all the other Martian environmental factors. This means that some failure modes will only become apparent once systems are operating on Mars. We'll discover that some materials degrade faster than expected in the actual Martian environment. We'll find that some components fail due to interactions we didn't anticipate. We'll encounter problems we couldn't predict or test for. This is normal in engineering. Real-world deployment always reveals issues that testing misses. But on Mars, discovering a critical failure mode could be fatal. There's also the human factors dimension of reliability. Systems must be designed so that tired, stressed humans make fewer errors. Interface design, warning systems, procedures, and training all affect how reliably humans operate systems. The 3 Mile Island nuclear accident, the Chernobyl disaster, and numerous aviation accidents resulted partly from human system interface problems. Situations where the design made it easy for humans to make critical errors or difficult for them to understand what was happening. Mars colonists would be operating complex, interdependent systems while coping with psychological stress, potential cognitive impairment from radiation exposure, fatigue from sleep disruption, and the constant pressure of knowing that mistakes could kill themselves and their colleagues. Systems must be designed with these human limitations in mind, but human factors engineering is challenging even on Earth, with extensive user testing and iterative design refinement. Challenge number 10, the sustainability question. Even if we overcome all the previous challenges and establish a Mars colony, can it ever become truly self-sustaining, or would it remain forever dependent on Earth? Self-sustainability means the colony can maintain and reproduce all the technology, infrastructure, and resources it needs without imports from Earth. This is a vastly more demanding requirement than simply keeping colonists alive with regular resupply missions. It means the colony must be able to manufacture everything from computer chips to pharmaceuticals, from spacesuits to solar panels, using only resources available on Mars. Consider the supply chain for something as simple as a smartphone. It requires rare Earth elements mined in various locations, refined using complex chemical processes, silicon purified to extraordinary levels and fabricated into microchips in multi-billion-dollar fabrication facilities, plastics derived from petroleum, glass manufactured from silica, metals extracted and refined, and assembly in factories with precision robotics and quality control. The supply chain spans dozens of countries and represents centuries of accumulated industrial knowledge. Could a Mars colony of even 1,000 people recreate this? Could they mine the necessary materials, refine them, manufacture components, and assemble products? The answer, realistically, is no, not for many decades and probably not for many generations. The industrial base required for modern technology is simply too large and complex for a small, isolated community to reproduce. This means Mars colonies would remain dependent on Earth for critical technologies, electronics, advanced materials, specialized tools, medical equipment, pharmaceuticals, and numerous other manufactured goods. This dependence creates vulnerability. If Earth decided to stop supporting the colony, if supply missions became too expensive, or if political priorities shifted, the colony could face existential crisis. There's also the question of what Mars offers Earth in return. Trade requires that both parties benefit. Earth would be supplying technology, equipment, and manufactured goods at enormous cost. What does Mars provide that justifies this expenditure? Raw materials don't make economic sense given the transportation costs. There's no obvious product or service Mars could export to Earth that would generate revenue sufficient to pay for imports. Some theorists propose that Mars could eventually develop unique technologies or scientific knowledge that would be valuable to Earth. Perhaps technologies developed for surviving in harsh Martian conditions would have applications on Earth. Perhaps scientific discoveries on Mars would justify the investment. But these are speculative and wouldn't address the fundamental economic imbalance for decades or centuries. Another approach to sustainability is to reduce dependence on complex technology by using simpler, more maintainable systems. Instead of advanced electronics, use mechanical systems. Instead of complex chemical processes, use simpler biological or physical processes. This approach might make a colony more self-sufficient, but it would also mean accepting a lower standard of living and reduced capabilities. Historically, isolated communities often experience technological regression. Viking settlements in Greenland lost technologies like metalworking over generations as they became isolated from European trade networks. Easter Island civilization declined partly due to resource depletion and isolation. Tasmania, separated from mainland Australia by rising sea levels, lost technologies like bone tools, fishing, and cold-weather clothing over thousands of years. These historical examples involved populations that were larger than any proposed Mars colony and existed in environments far more hospitable than Mars. Yet they still experienced technological regression when isolated. A Mars colony, even more isolated and in a far more hostile environment, could face similar pressures towards simplification and technological loss rather than advancement. Population size affects sustainability through the concept of minimum viable population. Small populations face genetic problems, inbreeding, genetic drift, and inability to maintain genetic diversity. They also face knowledge problems. There aren't enough people to maintain all the diverse skills and knowledge needed for a complex technological civilization. Anthropologists estimate that minimum viable populations for technological civilizations might need to number in the tens of thousands or even hundreds of thousands of people. This is because maintaining complex technology requires a diverse base of specialists, engineers, scientists, technicians, craftspeople, doctors, teachers, and many others. A small population can't maintain this level of specialization. Everyone has to be a generalist, and specialized knowledge is lost. A Mars colony of a few hundred or even a few thousand people would struggle to maintain the knowledge base of human civilization. They'd have to prioritize what knowledge and capabilities to maintain and accept losses in other areas. Over generations, they might become very good at surviving on Mars, but lose capabilities in fields not directly relevant to survival.